Hello, guys. Welcome back to Maths Zone African Motives. We are going to consider a typical revision for our Electrotechnics N4. And this is the November 2025 exam that we are going to look into. So, what you're going to do, watch according to the playlist, all right? Use the playlist so that you can have all the questions from the question one up to the end. So, in this platform, I'm just going to focus on question number one, which is on the principles of what? Electricity. So the first part that we are given on 1.1, you are given to choose an item from column B, all right, that matches a description in column A. So your answers must be from column B, which matches the description that you're given there. Write only the letter A to K next to the question number, all right, in the answer book. All right, so we're just gonna write the letters. All right, let us start with 1.11. The ability of a system to store an electric charge. The ability of a system to store an electric charge is actually the capacitance that you're referring to. So in our case, on these answers, yes, we have capacitance here on E. So meaning to say the best answer was going to be what? Capacitance. 1.12, the algebraic sum, all right, of voltage drops, all right, the algebraic sum of voltage drops in a closed circuit, the algebraic sum of the voltage drop in a closed circuit is equal to the algebraic sum of the applied EMF, all right? So this is our Kirchhoff's voltage law, all right? Kirchhoff's voltage law when you're dealing with the voltages. So here they gave us as the second law. So remember the first law is about current and the second law is the one for the voltages. So the best answer was going to be what? On J, all right? 1.13, the magnetic field, all right, or entire quantity of magnetic lines surrounding a magnet taken as a whole, what represent? That's the magnetic flux. The magnetic what? Flux. And we have that one. Yes, we have it. Magnetic flux on what? On A here. This is our magnetic flux. All right. Then another part, 1.14. We are given the opposition offered to the establishment of magnetic lines of force in a magnetic circuit. The opposition offered, that's reluctance. Yes, this is reluctance, guys. And we have reluctance here on F. So that is F here. 1.15, they become brittle in if their temperature is allowed to exceed 100 degrees Celsius. All right. What is it? This is paper and cotton. What else, guys, that we have here? So it's going to be what? Paper and cotton. That is the best answer that you're going to have. And on 1.16, we are given the direction of an induced EMF. All right. Is always such that it tends to set up a current opposing the motion or the change of flux responsible for that EMF. This is from our magnetism and electromagnetism. This is the Lenz's law, isn't it? The Lenz's law. Do we have that? All right. The Lenz's law. Yes, we have it on what? On B. So that is the best answer for this one. B, the Lenz's law. All right. That is what we have on that. Then 1.17, when the change in flux conditions is due to changing current conditions within conductor cell itself within the conductor itself, that is self-induction within the conductor itself, so that is self-induction, and that is what G. And they are somehow similar in construction to paper dielectric capacitors. Which capacitors do we talk about? Electrolytic is similar to that. So you can use, and that is the one that we are given only here. So sometimes even if you do not know the answers, we're seeing we are talking about capacitors, and this is the only type of a capacitor that we have, electrolytic what type. And 1.19, an induced EMF X to oppose the change that produces it. A self-induced EMF is in such a direction as opposes the change of current, as opposes what? The change of the current in the circuit in which it is induced. All right? An induced EMF acts to oppose. All right, it acts to oppose. I was not getting this statement properly. All right, acts to oppose the change. So that is going to give us the back EMF, this one, the any induced EMF that acts to oppose the change that produces it. A self-induced EMF is always in such a direction that opposes the change of current in the circuit in which it is what induced. So that is the condition of the back EMF. All right, the back EMF, do we have that? Yes, back EMF, we have it, which is H. So the best answer was going to be H. Then we have 1.110. H is equal to the MMF over the length, Ni over length. All right. So what is it? Like maybe they're just asking us for the formula to say what does this H represent? It is the magnetic field strength, or it can be referred to, we can refer to this one as the magnetizing force, magnetic field strength or magnetizing force. So which one that we are given? That's the best answer is going to be magnetizing force, which is D. All right, that is the best answer, was going to be what? D. Or we are saying it is what? The magnetic field strength as well. So that is what you were given. That is what you were given, and that is what you needed in order of answering this part. All right, let us move on to another part of our question number one. This was 1.2 of your question. This was 1.2, where we are given a resistor as an unknown value and a resistor of an unknown value and a resistor of 30 ohms are connected in what? Parallel. So these two resistors are connected in what? In parallel. A resistor of unknown resistance and another one, they are being connected in what? In parallel. So this is the condition. This one of what? Of 30 ohms. Just going to call it 1, so that this is R1. 30 ohms. You just number the way that you understand, all right? And a load of 15 watt, which draws a current of 5 amps, is connected in series with the two resistors. So we are going to have a load here. That is our load. And this load has power, 15 watts, and it draws a current that is 5 watt, 5 amps. So the current that it draws definitely is from what? It's from the supply, meaning to say it is the same current that entered what? the parallel circuit and branched into those two to the unknown resistor and another one to resistor 1. So that is the condition. Calculate the value of the unknown resistor if the circuit is connected across a what? A 45 volt DC supply when it is connected. So this is part of our electric circuits, all right? It is connected across what? A 45 DC. What will be the value of the unknown resistor, Rx? It's in parallel. All right, what we can do is to play around, just play around with the question, guys. Ask yourself, what is it that I can obtain from the given information? We can have, remember, in parallel, the voltage drop is the same, the voltage in parallel is the same as the voltage across resistor 1. It is the same as the voltage across the unknown resistor. Let's just go Vx. It is the voltage that is the same in parallel. We can have the voltage from the load, this resistor, that can help us to find, let us call it, we can just call it R2, no matter that you want, you can call it R2 or you can just call it RL since it is the load. So we can have, in this case, we can obtain the voltage across the load, all right, from the power. Remember, power in terms of voltage. Power is voltage times what? Times current. So it's voltage across the load and the current across the load. So you can find the voltage so that we can have the voltage drop of the parallel circuit. Remember these two, the voltage of the load and the voltage of the parallel circuit gives us 45. So we can simply work with that one. So let us find VL, the one across the load. So VL is going to be power over current divided by current. So we have the power 15, the current is 5. So that was going to give us what? 3 volts. So meaning say the voltage across here is 3 volts. What about the voltage in parallel? Because we know that voltage is the same. The supply here is the same as V parallel plus V load. All right. If we add voltage drops, these two give us what we have on the supply. So meaning to say Vs minus VL is equal to V parallel, where Vs is our supply. Yeah. Our supply 45. So 45 minus 3 is going to give us V parallel. So our parallel voltage was going to be 42 volts. So this is what we have here, 42 volts. So using that, it is easier for us to obtain this resistor because we know that the load, the current that it draws of 15 amps is the same current that is going to enter here as our supply current, 5 amps, is going to be shared between these two resistors. So they are sharing 5 amps. So we can take advantage of that to say, since they are sharing the same current, it means I1 can be determined. Then we can calculate IX for the unknown resistor. So find I1 voltage over what? Over resistance. So it's voltage in parallel over R1. In parallel, our voltage is 42 over R1, which is 30. So this is going to give us the value of I1, which is 1,4 amps. So if here we have got 1,4 amps, which is entering this resistor, what about the one going to the unknown resistor? IX is simply the supply minus this from our Kirchhoff's, right? Or you can just understand, guys, this is entering, these two are going out. So they are sharing 5 amps. So simply the supply minus I1. So that's 5 amps minus I1, 1,4 amps. And this was going to give us 3,6 amps. So this is the current that we have on the unknown resistor. So you're asking yourself, why is it that we have to calculate current? Because remember, we have got the voltage, which is the same here, which is what? Our V parallel, 42 volts. So if I have voltage and current, it's easier for us to determine what? To determine the resistance. So therefore, the resistance of the unknown, our Rx is going to be V parallel over current, voltage over current. We have the voltage of 42. What is our current? Our current is 3.6 amps. So this is going to give us the resistance of the unknown resistor, 11.667 ohms. That's our unknown resistor. So that is the idea. So this type of equation, guys, you can answer it in many ways. Many ways. Just go back through that part of your electric circuits. Understand the basics. It's just about basics. All right, basics. So that is what we had. Let us move on to another part. If you check, I have illustrated this question. I have illustrated this. I think it's on under membership or what, but I've illustrated this type of a question where you are given under your magnetism and electromagnetism, and it also has some properties of our resistivity. We are given that a coil has got 300 turns. The number of turns is what? 300 of a conductor, sorry, with a cross-sectional area of 0.2 square millimeters. So that's times 10 to the exponent of -6 to square meters. And the mean length per turn, the mean length per what? Per turn, guys. Take note of what you're given there. It's 150 millimeters per watt per turn, which is in meters divided by 1000. That's 0.15 meters per each turn. So what is our length? Our length is going to be the mean length, 0.15 meters per turn, times the number of turns. How many turns do we have? 300 times the number of 10. Do not forget this, guys. All right. So they always try by all means to confuse you guys. So this was going to give us 45 meters. Remember, we converted this to what? To meters. So that's the length, 45 meters from the mean length per 10, per each, 1, 2, and so on. What if they're 300? Multiply by what? 300. Here's an inductance of what? 0.3 henries. Calculate the following: 1.31. The resistance of the windings. If the specific resistance of the conductor is, all right, what is the resistance if our resistivity of the given winding is what? 0.025 micro henries per what? Micro ohm meter, micro ohm meter. Micro times 10 to the exponent of what? -6. So like I said, it is just a continuation from our resistivity concept, all right? I needed this part, sorry for that. I needed a part where I've got my formula sheet here. If you check under your resistivity, we have resistance taken from resistivity times length over what? Over area. Do not forget all those basics. All right, so let us apply that. We have our resistance. Since there is given, we are given resistivity of the given material. So that's length times area. Resistivity 0.025 times 10 to the exponent of -6. The length 45 meters over the area in square meters 0.2 0.2 times 10 to the exponent of what? -6. So that was going to give us the resistance of 5.625 ohms. So just like that, you are done. So you see, guys, electrotechnics is just a basic subject, basic. Just follow the formulas as they are. Just understand all the basics and so on. Then what is going to be the average value of what? The EMF induced in the coil when a current of 6 amps is reversed. When a current is reversed, I simply add that or multiply by what? By 2. So that's 12 amps in time frame of 0.4 seconds. So we are to calculate E, induced EMF. Given inductance, How can we determine the value of E? We have inductance. So we can play around with this formula from inductance, change in current over what? Over time. So it's simply inductance times current over what? Over time. Just like that. So that is how we can play around with this question to find our E. So we saw that inductance times current times what? Time. What is our inductance? We have it 0.3 times what? Our current 12 amps. It is being reversed over the time of 0.4. So that was going to give us the induced EMF of 9 volts. All right. So it's all about revision, as you can see. Just revising, guys. Here we are not giving notes. It's just about revision. Let us consider another part. We are given that a bakery oven dissipates this energy. All right. So we have got the amount of energy, which is our Q. So Q is our energy, 160 megajoules. All right. During 3 hours, the time frame, 3 hours, which is in seconds, multiplied by 3,600. That's 10,800 seconds of operation. If the oven is supplied at the given voltage of 250 volts, calculate 1.41, the resistance of the element. The resistance of what? The element. So how can I find the resistance? Simple, guys. I have the energy, and energy is the power times what? Power times time, where time is in seconds. And power can be expressed in voltage times current, V squared over R, I squared times what times R. So you look into the power, which formula can you substitute here to calculate the resistance? I have voltage, I need resistance. So the formula I'm going to use is V squared over R, where there is voltage. I do not have current, guys. So I cannot use this one. I cannot use this one also because I do not have current so far. So meaning to say, in place of the power formula, substitute. Power is also written or given as V squared over R times what? Times the time. Just like that. Make the resistance the subject of the formula as you are asked. All right, so let us make this one the subject. This is over 1. So QR is equal to V squared T. So we want R divided by what? Divide by Q. So R resistance is V squared times T over what? Over Q, just like that. Voltage of what? 250 squared times the time in seconds. Here time, here is in seconds. Take note. So that T must be in seconds. 10,000 what? 10,800. In what? In seconds. Be very careful. Over what? The energy. 160 megajoules. 160 times 10 to the exponent of 60. Times 10 to the exponent of 6, I mean. That is going to give us the resistance of what? The element. 4,21875. Which is going to be 4,219 ohms. Just like that, we have our resistance. All right, so in case we're going to need this resistance, please take note of the value. Take note of the value. Let us consider another part of our question. All right, just to finish up. All right, then we are given on 1.42 to calculate. All right, everything is under calculate here. The cost to operate the oven. So we need what? The cost to operate the oven for a month. For a month. In 1 month. If the oven operates for what? 5 hours per day. So the oven operates 5 hours per day, each day. 5 hours. For what? For 30 days. In a month. For 30 days. For 30 days. So we are asked to calculate this. If the unit charge of 1 rand 85 is given. So our unit charge is what? 1 rand 85. So remember that the cost, guys, is simply the unit charge times kilowatt hour x times kilowatt hour, where x is what? The unit what? The unit charge. So that's the unit charge times what? The kilowatt hour. So I have the unit charge already. What I need is what? Kilowatt hour. Kilowatt hour, guys, means power in kilowatts times the time in hours. Kilowatt hour. So do we have the power that is measured in kilowatt? We do not have the power. So find the power first. From where? From that formula that we had before of what? Our energy. Q is equal to PT. So find what? Find P first, the power. So power is energy over what? Over time. From this formula, take note that time is in seconds. So when you substitute, you must substitute the time in seconds. 160 times 10 to the power of 6, our energy over the time, 10,800 in what? In seconds. From this formula, guys, to obtain these megajoules, you must have your time in what? In seconds. So that is the idea about that, guys. So this is going to give us the power, and that power was going to be 14814,814 like that in watts, but we need kilowatt. How do we convert this to what? To kilowatt hour. We simply have to divide by what? 1000, or multiply by 10 to the exponent of minus 3, the opposite of kilo. Just divide by 1000. So that is 14,81. This is going to change this one into 5 kilowatts. In what? Kilowatts. This is our power. But we need the kilowatt hour now, which is kilowatt times what? Times time in hours. For what? Here it was the energy, guys, gave us the power in that 3 hours. This is where we got the power. When we are talking about the kilowatt hour, it's no longer about that. It's about the time of the element that was being used. It was used for what? 5 hours a day. So in a day, our kilowatt hour in a day is going to be the kilowatt, 14,815 times 5. This is a day. A day. If you're talking about for 30 days in a month, multiply by 30. All right? So this one is in a what? In a day. But we are given that 5 hours per day in a what? In a month. Where is that one? Where did I write that month, guys? All right. Did I even? All right, here. In a month. For a month, we've got what? For 30 days, according to what we're given. So we have to multiply by what? By 30. This is for 30 days, a month. For a month now. So this is where, that is how we're going to find our kilowatt hour. 14,815 times 5 times what? 30. So this was going to give us 2,222 watt, 25. So we have kilowatt hour. Then use it now to determine the cost at a given unit charge of what? 1 rand 85. Multiply to the kilowatt hour for 30 days for that month. 222, 2,222, what? 25. That was the idea of this question, guys. All right. So we have the total cost from that. All right. Let us multiply this one as it is times 1,85. So this is what you're going to get: 4,111, 16 to 2 decimal places, 16 rand. So that is the cost in a month. All right. So that is a revision. Just a basic question, but you have to be careful, very, very careful. Calculations, especially on the time. The time that you use on the kilowatt is the time for the given what? That oven, to say the number of hours it operated in 1 month. It operated for how many hours? So that's 5 times what? 5 times that. This is for a month. Not 3. 3 was used to determine the power from the given information. This information was given hand in hand. So it just helps us to find what? To find the power. Only that, to find the power. And your power must be in kilowatts so that you can have what? The kilowatt hour. Kilowatt, it is just on its own, guys. Kilowatt. Convert your power to kilowatts. All right. So that is it. That was a basic question on our question number 1, principles of electricity, summing up to what? 30 marks, everything. So you see, guys, in exam, let's say you obtain these 30 marks. What do you need now? You just need 10 marks from other topics. Just 10 marks left. So you see, it's easier for you to get a distinction in your electrotechnics N4. So anyways, let us do revise as much as we can.